Oh, wow. Okay, good morning. Okay, so we have a couple of weeks left before we get to the end of the semester. So we're going to continue on today with looking at combustion analysis, which is sort of the next to last topic in the course. And so let's go ahead and begin with the idea. This is section 3.5. And it's called combustion analysis. Now, strictly speaking, it's more broad than this, but essentially for our purposes, combustion can be thought of as a particular type of chemical reaction. So it's a type of reaction. There are different types of reactions. When you get into Chem 11, you'll look more in depth at the different types of chemical reactions. But for right now, let's just consider combustion. Combustion is the case where you take something which is called a hydrocarbon, and you react it with oxygen gas. Typically oxygen gas. You can do it with oxygen, liquid oxygen as well. That's what rockets do. So SpaceX, for example, their rockets are powered with liquid methane and liquid oxygen. But for the most part, we deal with oxygen in the gas phase. And then the products of that, there generally are just two simple products. One of them is carbon dioxide gas. So this is CO2. And then water, either in the liquid phase or the vapor phase, gas phase. Vapor and gas essentially mean the same thing. So I'll put it in a liquid here, okay? So that's the general idea for a combustion reaction. Now, what's significant, or one of the things that's significant about combustion, is that it releases energy. And we talk about the causes of it releasing energy in chemistry 1100. You look at something called thermochemistry, which is the study of heat and energy. And then you look at chemical bonds and how breaking chemical bonds requires energy, and forming chemical bonds generally releases energy. Okay, so we'll talk more about that.
Professor, sorry, there's a message in the middle of your screen about this thing being recorded. That's covering what you're writing.
Covering it. Oh, that's odd. It's not covering it on mine. Huh.
It just says it just asks you whether to say continue or leave meeting.
Oh yeah. So are you able to, is that for you to click on?
No, it's well, I mean, I don't see why it would be for me, because I'm not recording, right?
Yeah, I don't see it on my screen.
Oh, that's so bizarre.
I don't see it on either the iPad or the computer screen. I don't see it anywhere.
Okay, no worries.
Unfortunately, you're the only one on here, so we can't get any feedback from anybody else. Here, let me do this.
Okay, it's gone.
It's gone now?
Yeah, it's gone.
Excellent. Great. All right, good. All right, so the idea then is that combustion is a hydrocarbon. So let me show you some examples of hydrocarbons. Perhaps the most famous one is methane.
So was it that it releases energy? Is that what you wrote?
Yeah, releases energy. That's the important thing, is that it releases energy. That's why combustion reactions are so important.
Okay.
So methane is CH4, and that's a hydrocarbon. A hydrocarbon has to have carbon and hydrogen in it. So if you look at the formula for methane, it has carbon and it has hydrogen. Another example of a hydrocarbon is ethane, C2H6. H6. Another one, propane. You've probably heard of propane. Many people actually heat their houses with propane. Propane is C3H8. Butane, if you've ever seen a lighter, clearly you've seen a lighter, right? These little disposable lighters, C4H10. Okay. Pentane, C5H12. Hexane, C6H14. And there are many of these types of hydrocarbons. These ones make a particular series. By the way, this is 14. These are called alkanes. And the name alkane ending in ane, if you take a look at the names of each of these different compounds, they each end in ane, right? Methane, ethane, propane, butane. They're all alkanes. And all of these follow a particular formula for their chemical formula, mathematical formula for their chemical formula. They follow the formula Cn, meaning some number of carbon atoms, H, 2n plus 2, meaning twice the number plus 2. So if you have one carbon, C1, right, the number of hydrogen atoms would be 2 times 1 plus 2, which is 4, right? So C1, H2 times 1 plus 2, that would be CH4, 1 carbon, 4 hydrogens. Well, that's methane. And all of these alkanes follow that particular format. So those are examples of hydrocarbons. Those are some. Another one you may have heard of is, well, let me just put a couple more here. I'm going to go ahead and write heptane, 7 carbons. And based on this formula, you could predict how many hydrogens will be in the heptane, because you have 7 carbons, 2 times 7 is 14, and then you add another 2, you get 16. So heptane is C7H16. The next one, you may have heard of octane. You may have heard of the octane rating, which is used when people buy petrol or gasoline. Generally, the numbers are somewhere in the high 80s into the low 90s. And octane is a particular compound that has 8 carbon atoms. So the number of hydrogens would be twice that. So that'd be 16 plus another 2. So you get 18. And I'm going to go ahead and go up to 10. No name, meaning 9, C9. 2 times 9 is 18, plus another 2 is 20. And then decane, like a decade, right? That's 10. Oops, sorry, I wrote decade. So that would be 22. Okay, so those are just some of the alkanes. Those aren't all the alkanes, but those are the first 10 alkanes that people might look at. Those are examples of hydrocarbons. Other examples, you may have heard of this one, is called benzene. Benzene is C6H6. Benzene is famous for various reasons. Another example, acetylene. Acetylene is used in what they call torches. It's called an acetylene torch. It's used for welding. Produces very, very hot flame, enough that you can actually melt metals in together. Acetylene is C2H2. Okay, so those are examples of hydrocarbons. Technically speaking, a hydrocarbon just has to have carbon and hydrogen. So if you have something that has oxygen or nitrogen as well, in addition to carbon and hydrogen, that could also be considered a hydrocarbon. Okay. Now, what we're going to do is we're going to look first at predicting the products of a combustion reaction. Okay. So imagine we have this combustion reaction. Between, sorry, I'm not writing that very well. I'm just going to pick one, hexane. and oxygen. Predict the products. Okay. What are the products of the reaction between hexane and oxygen? Well, here's hexane, C6H14. It's with oxygen, so you're going to react it with oxygen. And then the products of combustion are, there's two of them. The first one is carbon dioxide, and the second one is water. Okay, carbon dioxide and water. Those are the products of combustion generally. There can be some exceptions to that, but generally those are the products. And I'm just going to write over here just so you can see plus energy. And I'm not going to get technical about the issue of energy. That's something you cover in the next course. But combustion does also release energy, and that's why it's important. That energy can be used in a piston to drive an engine, to drive a rocket, to drive a jet engine, to produce steam, to boil steam. Boil water into steam so that you can heat up places. You can generate electrical energy from it by using a turbine. There's all sorts of things you can do with that energy, but a combustion reaction is the beginning of that process. So, I'm sorry, I wrote the wrong formula, C6H14, right? I said hexane, so C6H14, okay? So the formula for the hydrocarbon plus oxygen forms carbon dioxide and water. And then if you want to consider energy, you could also say that it produces energy or releases energy, okay? So that's the idea behind combustion. Now, what we want to look at is a particular, very specific set of calculations that we do with combustion analysis, and that is figuring out what's called the empirical formula and the molecular formula for the compound based on a set of data. So what I'm going to do, let me create a new slide here, is I'm going to give you, I'm going to take a look at a specific example from Alex. So this is called elemental. Different textbooks call this different things. So it's called elemental analysis of binary compounds. Okay, so the example in this particular problem, what they do is they say you have a compound, and they call it compound X, meaning that we don't know what this compound is. Okay, so we call it X for unknown, right? Has the following composition. Okay, they give you the name of the element. So there's two of them here. One is chlorine, and the other one is oxygen. And then they give you what's called the mass percent. Now, we talked about mass percent way back in section 2 of chapter 3. And then the question is, write the empirical formula for this compound X. Okay, that's the question. That's a very typical type of question. We look at these a lot in chemistry. What we're doing is actually pretty cool. What you're doing is you're taking some mass percent data and you're actually figuring out the chemical formula of the compound. Now, strictly speaking, you're figuring out what's called the empirical formula. So I want to point out, if you are given mass percent of the elements in the problem, and you're not given any other information, then what you're calculating is called the empirical formula. Okay, and I'll talk a little bit more about what that means in a moment, but after we do this calculation. But if you are not given any other information, just the mass percent, that's what you're going to calculate is the empirical formula. Okay, so here's how you go about it. If you note, if you look at these two numbers, they add up pretty close to 100%. It's 99.9%. Okay, so what I'm going to suggest you do in step 1 is assume that the percentages that are given are equal to the masses in the units of grams. Okay, that's your first step when you approach this problem. So for example, if chlorine has a mass percent of 38.7%, assume that you have 38.7 grams of that element. I'm going to write the symbol Cl, Cl for chlorine, right? Remember, C is carbon, Cl is chlorine, okay? Same thing for oxygen. If they tell you that you have 61.2% oxygen, assume that's the mass in grams. Okay, so O for oxygen. So now that's your first step. Just take the percentages and make them grams. Step 2, using these masses, divide by the molar mass of the element to find the number of moles of that element. Okay? So chlorine and oxygen are the two elements that we're dealing with here. So we divide by the molar mass. So let's do chlorine first. 1 mole of chlorine has a molar mass of 35.45 grams. That's from the periodic table. So I'm dividing by the molar mass to get the number of moles. That's what we did back in section 3.4, which is still pretty recent. We've only just done that last week. But dividing by the molar mass gives you the number of moles. Oops, I know I did that wrong. 38.7 divided by 35.45 is 1.0917 moles of chlorine. Okay. Same thing with the oxygen. 61.2 grams of oxygen. 1 mole of oxygen is 16.00 grams. From the periodic table, you're dividing by the molar mass. So 61.2 over 16, and you get 3.825 moles of oxygen. Okay. That's kind of interesting. All right, next step. So we've done 2 steps so far. The first one is to assume that the percentages are equal to grams. The second step is to find the number of moles of each element using the molar mass by dividing by the molar mass. Okay. So let me make a little room here up at the top. Okay, step 3. Divide the moles of each by the smaller amount. Okay, so you're going to do two calculations here. For each one, you're going to divide by the smaller amount. Now, the smaller amount is chlorine, right? 1.09 is smaller than 3.825.
Professor, sorry, where did you get 35.45 and then 16?
Periodic table.
So that's the number at the bottom, is it?
Usually. It depends on how the table is designed. Different people have different artistic aspects of it, but usually it's the one below.
Okay. So yeah, so on Alex, okay, all right.
Sometimes it's a little bit off to the left, sometimes a little bit off to the right. It just depends who made the table. Typically, it's the bottom one, though.
Okay, thanks.
Yeah. So we divide by the smallest. So let's do so chlorine's the smallest. So we're going to do chlorine first. So chlorine has 1.0917 moles. And we're going to divide it by the smallest, which is chlorine, 1.0917. Well, that's going to give you 1, right? So when you do this step, one of the elements will always be 1 because you're dividing it by itself. You're dividing each of them by the smallest. So anything divided by itself is 1, with the exception of 0. But oxygen is not going to give you 1, right? Because you're going to take 3.825. And I'm going to go ahead and write the symbol in here just so you can see. So again, you're dividing by the smaller one, okay? Now, this may give you a number that's really close to a whole number, or it might not. So we have to be very careful when we interpret this, but the calculation is straightforward. Just put in your calculator, 3.825 over 1.0917. And notice you get 3.504. It's unitless because it's moles over moles, okay? Now, what I want to do is I want to look at this number here. This number is not a whole number. So this one's a whole number, right? 1 is a whole number. But 3.504 is not. So here's what you do in step 4. You evaluate the one that's not a whole number. You look at the digit that comes after the decimal point. You're going to just look at that first number after. Ignore everything that comes after that, right? If it's 0, okay, so if that number is 0, then you can round it to 3. So if this came out to 3.004, you could just round it to 3. If it came out to 4.012, you could round it to 4. But that first digit past the decimal point is not a 0. So that means you cannot round it. Okay. So in step 4, if you get a number in which the first number past the decimal point is 0, round to a whole number. So you get 3. And then that makes the problem very easy. If you get a number where it's not a whole number, I mean, it's not a 0. So it's 0.5, for example. Don't round. Okay. We have to do another step. So if, I'm going to write this here, then you have to do step 5. Okay. If it is a 0, you're done. You got the problem done. Now, most likely, Alex is going to give you problems where it's not a 0 because they're trying to make it challenging for you. Some textbooks, it'll be a 0 and you would just round it to a whole number. You'd be done with the problem right there. Essentially, you'd be done. But that's not going to happen with Alex. They're going to give you problems where you have to do some arithmetic now. Okay. So 3.5, that's really what we're looking at here. So let me erase this here. And we're going to go on to step 5. So we have, I'm going to write down the numbers again. For chlorine, we have 1. And then for oxygen, we have 3.504. Now, here's the sort of little background mathematically. And let's talk a little bit. I'm going to erase this whole thing, actually. When we're dealing with numbers, when it comes to chemical formulas, here's the issue. Chemical formulas have to be whole numbers. So for example, Cl2O7, right? That's a chemical formula. Cl2O3.5 is not a chemical formula. It's generally considered poor form. So we need to have whole numbers as the subscripts. So this one's invalid. This is not what we would write. Now, there's, when you start getting into complicated issues, sometimes we do allow that. But for the most part, we want to have whole numbers, okay? This is not a whole number. So how do we deal with that? You write the formula with the numbers you calculated. So I'm going to write it as Cl O 3.5. And notice I'm just going to go one digit past the decimal point. So we have 1 chlorine and 3.5 oxygens. We want it to be whole numbers. So here's what you do. You multiply each of the subscripts by the smallest possible number that you can, so that each of these subscripts becomes a whole number. Now that sounds a little odd, but here's what I mean. If I take 1, this is a 1, even though we didn't write 1, it's implied that it's a 1, and this is 3.5. We ask ourselves, what number would we have to multiply that by so that they're both whole numbers? And we want the smallest possible. Well, if I multiply, let's take the smallest whole number possible, 1. If I multiply 1 by 1, I have a whole number, so that's good. But if I multiply 3.5 by 1, I don't have a whole number. I still have a fraction. I still have a decimal number, right? So 1 is no good. So we just step up to the next level, 2. What happens if I multiply by 2? Well, 1 times 2 is 2, so that's a whole number. 3.5 times 2 is 7. So if you multiply them both by 2, you now have 2 whole numbers. And that's what we're going to do. We're going to multiply each of them by 2. So you get Cl2. 3.5 times 2 is 7. So now you have O7. Now we have a valid chemical formula. This is good because we have whole numbers. Now you might say, well, wait a minute. If you're multiplying by 2, doesn't that change it? And the answer is yes, it changes it. However, the ratio of chlorine to oxygen is still the same. We haven't changed the ratio of those 2 elements. 1 to 3.5 is the same ratio as 2 to 7. So by changing the chemical formula from 1, 3.5 to 2 and 7, that's a valid step to take because it has the correct ratio. And this ratio is called the empirical formula. Okay, Cl2O7 is what we call the empirical formula. Okay, so it had a lot of steps. It's a kind of challenging but fun problem. Let me show you another example. Okay, here's one. So this one, the elements given are carbon. So that's element C, right? And it has a mass percent of 74.8. And then you have hydrogen, H, 25.1%. Okay. So same thing, we're going to find the empirical formula of compound X. Okay, so step one, assume that these percentages are grams. So I'll do that over here. I'm just going to write that this is 74.8 grams of carbon. And this one right here would be 25.1 grams of hydrogen. Okay. Now, step two, you divide each of them by their respective molar masses. So hydrogen is element number 1, and its molar mass is 1.01. Carbon is element number 6, and its molar mass is 12.01. Okay, so let's do carbon first. We have 74.8 grams of carbon. We're going to divide by the molar mass. Okay, remember the molar mass is the mass of 1 mole, and it's in grams. So 74.8 divided by 12.01, and you get 6.228 moles of carbon. Do the same thing for hydrogen. 25.1 grams of hydrogen. 1 mole of hydrogen is 1.01 grams. Okay, so 25.1 divided by 1.01, and you get 24.85 moles of hydrogen. Okay. Next step, divide each by the smaller number. This one's the smaller one. So that's the one you're going to divide by. So we're going to do carbon first. We're going to divide it by itself, right? Because it's the smaller one. And like I said, you're always going to get one of these will be 1. It has to be because you're dividing it by itself. Then you do the hydrogen. Hydrogen is 24.85. Divide that by 6.228, divide by the smaller. And now you're going to get a number that's actually pretty close to a whole number. Let's take a look at it. 24.85 divided by 6.228, and you get 3.990. That, if you round it, so you're looking at this number here, it's 9. If you were to, if you are really, really close to a whole number, you round it to the whole number. Okay. So 3.99, if you were to round that to 2 sig figs, you would get 4.0. 4.0 is essentially a whole number. So there's our answer there. Now, this one, we don't have a 0.5. So if you don't have a 0.5, we don't have to do the step where you're multiplying by 2 to turn that 0.5 into a whole number. So now we can just write them just as they are. You have 1 carbon. And remember, in chemical formulas, if it's a 1, you don't write 1. We don't write C1 or H1. We just write C or H. If the number is greater than 1, 2, 3, 4, 5, then we write it as a subscript. And if you take a look, this is the compound we talked about earlier. This is our methane molecule, CH4. Right? That was the first hydrocarbon in our sequence. So this one, this example is a little easier than the one we just did because we didn't have to multiply everything by 2. Okay. Let me see. Are there any where they have you do? I don't think so. Okay, good. Now, let me show you the second type of problem. So that's the first type. The second type is where you're going to find the molecular formula from the molar mass. And elemental analysis. Okay, so that's your second type. So in this one, what differs is they give you another number. And what they're going to do is they're going to say this compound has a molar mass of 316.29 grams per mole. That's the key to this one. They're going to give you an additional piece of information. And that's why we're going to find the molecular formula. So the previous one was we were going to find the empirical formula. This one we're going to find the molecular formula. And I'll talk more about the differences between those two. But I want to go over this problem. I want to make sure you see how to approach this problem. And essentially, you're going to approach it the same way you did before. It's the same as the previous problem. We just have an additional step at the end. Okay? So step one, assume your percentages are grams. Phosphorus is P. Okay? Remember, fluorine is F, phosphorus is P. Sulfur, 60.83 grams. So same thing as we did before. We're not changing the approach here at all. It's only at the end that this will be different. Now, let's look up those elements in the periodic table. Phosphorus is element number 15, and it has a molar mass of 30.97. Sulfur is actually right next to it. It's element number 16, and it's 32.07. Okay, so they differ by a little more than a gram per mole. Sulfur is a tiny bit heavier than phosphorus. Chemically, they're actually a little similar, phosphorus and sulfur. Kind of interesting elements. Okay, so we have the masses. So what's our next step? We have the masses. We divide by the molar mass to get the number of moles, just like we did. So 39.17 grams of phosphorus. 1 mole of phosphorus is 30.97 grams. Okay, so it's going to be a little more than a mole. 39.17 divided by 30.97, and you get 1.265 moles of phosphorus. Do the same thing for sulfur. Oops. There we go. Okay. Let's do the same thing for sulfur. We got 32.07 grams of sulfur. 1 mole of sulfur is 32.07 grams. Okay. So 32, oops, I made a mistake here. 60.83. There we go. So 60.83 divided by 32.07, and you get 1.897 moles of sulfur. Okay, so far so good. Same thing. Divide each by the smaller number. Okay, so I'm just kind of looking at this ratio. I'll talk a little bit more about ratios in a moment. Phosphorus is the smaller one. So let's do phosphorus first. You're going to divide it by itself because it's the smaller one. That's going to give you 1. Let's do the sulfur. 1.897 divided by 1.265. Now, this number, let's take a look at it. 1.897 divided by 1.265, and you get 1.4996. Okay, so now look at that first digit past the decimal point. That is not a 0. right? It's not close to 1.0. It's not 1.99 either, so it's not close to 2. In fact, it's almost exactly halfway between 1 and 2, right? So what number is halfway between 1 and 2? 1.5, 1.5. In fact, if you round this to 1 digit past the decimal point, you get 1.5. So that tells us the ratio is really 1.5. So now this is where we had that first example that we did with the chlorine and the oxygen. We have phosphorus. I'm just going to go ahead and put a 1 there just for now, and then sulfur 1.5. And then we ask ourselves, what would you have to multiply that 1.5 by to get a whole number? You'd multiply it by 2. So if you multiply each of them by 2, you get P2. 1 times 2 is 2. 1.5 times 2 is 3. And so you have P2S3. And that is your empirical formula. Okay, that's the empirical formula. That's what you're looking for if you were just doing the empirical formula. In fact, this particular problem is exactly like the empirical formula, except we have one more step. So I circled up here molecular formula. The molecular formula, they got to give you an extra piece of information, and that's right there. So that is connected to that term right there. Okay, so what I'm going to do is, let me save this, is I'm going to write our numbers down again. So let's come back here. We're going to say we have, oops, come on, let's do a new one. So here's our molecular molar mass. Okay, I'm sorry. Let me come back here. It's 316.29. So this is given information. And now we also have our empirical formula. We just figured that out. Our empirical formula was P2S3. Okay. Now we want to find the molecular formula. Okay. How do we find the molecular formula from the empirical formula? So here's the thing that I want to point out. If you have the empirical formula, I'll write that as EF. If you want to find the molecular formula, you need the molar mass. So in this particular example, we have that, right? We know the empirical formula. We know the molar mass is 316.29 grams per mole. That will allow us to find the molecular formula. Before I do that calculation, I want to show you quickly what the difference between the empirical and molecular formula is. It turns out that historically, chemists were able to figure out empirical formulas before they were able to figure out molecular formulas. It was a difficult step to go from the empirical to molecular. What you can do is very simple experiments. You can take something, put it in a little porcelain dish, heat it to the point where it breaks apart and gives off gases. And from measuring the masses before and after, you can figure out what the empirical formula is. But you can't figure out the molecular formula that way. So there was a big stumbling block in figuring out molecular formulas instead of empirical formulas. So let's talk about what the differences are. The empirical formula is really not the formula for the compound. It's the ratio of the elements. It's just a ratio in the compound. So for example, we might say that there are 2 hydrogens for every 1 oxygen. We might say there's 2 hydrogens for every 2 oxygens. It's just a ratio, how many of one element compared to the other. We might say, for example, it's 1 carbon for every 2 hydrogens for every 1 oxygen. Okay, that would be the empirical formula. So that's what we've been calculating thus far. We're just figuring out what the ratios are. But the molecular formula is more useful in many cases. This is the actual number of atoms in the compound. So for example, glucose. Glucose is C6H12O6. It has 6 carbons, 12 hydrogens, and 6 oxygens in one molecule. That is the molecular formula right there. It's not just the ratio of how many carbons and hydrogens and oxygens are, it's the actual number. So that's a very useful thing if we want to figure out all kinds of things, knowing what the actual compound is. The empirical formula isn't that same information. It's just the ratio. So for glucose, the molecular formula is C6H12O6. That's the actual number of atoms. But the empirical formula would just be CH2O. This is the empirical formula. It's not the actual number of atoms. It's just the ratio 1 to 2 to 1, right? This is 1 to 2 to 1. Whereas the molecular formula, it's the same ratio. 6 to 12 to 6 is the same as 1 to 1, 1 to 2 to 1, but it's the actual number of atoms in the molecule. Okay, so what we want to do then is we want to use this molar mass to do that last step, to make the jump, the leap from the empirical formula over to the molecular formula. And it's actually a very simple calculation. You just have to know how to use the numbers. So let me show you how to do it with this phosphorus and sulfur problem. Okay, here's what you do. You take your empirical formula, which is P2S3, and you calculate the molar mass. Calculate what the molar mass of that compound is. So let's go ahead and do that. Phosphorus is 30.97, and there are 2 of them in the empirical formula. Sulfur is 32.07, and there are 3 of them. Okay, so you add those together. So 2 times 30.97 plus 3 times 32.07, and you get 158.15 grams per mole. Okay, so that's your first step in this calculation of the molecular formula. Step 2, you divide the given molar mass by the molar mass you calculated, which is the empirical formula, EF. Okay, so you're going to take the one they gave you, because this is for the actual compound, and you're going to divide it by the molar mass that you just calculated, the empirical formula. So let me write it this way. You're going to do the molar mass of the molecular formula, that's given, divided by the molar mass of the empirical formula. So 316.29 divided by 158.15. Okay, so 316.29 divided by 158.15, and you get 1.999. Actually, I got 4 nines. Now, let's take a look again. See how that's a 9? That's very close to 2. So we're just going to round that to 2. What that's telling us is that this number here is twice what this number is here. It's 2 times as large. Now let's use some logic. If something is twice as heavy, that means it has twice as many atoms, right? If 1 carbon atom weighs 12 grams, 12.01, 2 carbon atoms would weigh twice that, 24.02. So if this is 2 times as heavy as this, it means it has 2 times as many atoms. So what do? You just say, hey, we already know what the empirical formula is. It's P2S3. We know that it has to have twice as many atoms, so you just multiply it by 2, and you get P4S6. And that is your molecular formula. Okay? So we now have an answer. The empirical formula is P2S3, but in this particular example, they want us to get the molecular formula, the actual formula of the compound. That would be P4S6. So let me show you a little drawing. It's actually kind of P4, so probably oops, sorry. Let me do this again. It might be something like this. P4 S6, right? P4S6. So S, 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 S. So it might be something like that. This is the molecular formula. Okay, P4S6. So there's 6 sulfurs for every 4 phosphorus. Now, that's the molecular formula. The empirical formula was P2S3, right? So that one is not the actual formula. It's not what the actual number of atoms in the compound is. It's just the ratio. It's the smallest ratio you can get. It's just 2 and 3 is the same ratio as 4 to 6. So let me show you another example. Got time for one more. Let's do this one that has oxygen. So in this one, again, they're going to give you information about compound X. And it has a molar mass of 283.89. So there's your molar mass. That's given. And then they give you information about the compound. They say you have phosphorus in it. And phosphorus is 43.64% of the mass. Okay, so, and then the other one is oxygen in this case. So oxygen is 56.36%. Okay. And they want you to find the molecular formula. So a reminder, what you do is you do the empirical formula first, just like we learned at the beginning, and then you do the molecular formula. Okay, do in that order. Okay, so step 1, assume that this is grams. Okay, so we have the masses in grams. Step 2, divide by the molar mass. The logic here is that by finding the number of moles, you're figuring out how many there are. And this is it's sometimes a difficult concept for people. The mass cannot tell you anything really about the formula because the elements don't weigh the same. So if I said I have 6 grams of carbon, and then I said I have 12 grams of carbon, from that I could say I have twice as much carbon, right? There's twice as many atoms because I have 12 versus 6. But if I say I have 6 grams of carbon and I have 12 grams of oxygen, you can't tell how many you have relative to each other because they have different weights. 16 grams per mole for oxygen, 12 grams per mole for carbon. So if you have different elements, which is what a compound has, you can't figure out anything about how many there are from just the masses. You've got to have the number of moles. Remember, a mole is a number of atoms. So if you know the number of moles, you know the number of atoms. So that's how we can tell chemical formulas. Chemical formulas are telling you how many there are, not how much they weigh. So step 1, get it into mass in grams. Step 2, figure out the moles. So remember, this is phosphorus and this is oxygen. So if you have 43.64 grams of phosphorus, 1 mole of phosphorus is 30.97 grams. Okay, so 43.64 divided by 30.97 is 1.409 moles of phosphorus. Do the same thing for oxygen. 56.36 grams of oxygen. 1 mole of oxygen is 16.00 grams. So 56.36 divided by 16 is 3.5225 moles of oxygen. I went out another extra sig fig because it ended at 5, so I went ahead and wrote it down. Make sure you don't do any rounding yet. Don't do any rounding in these stages. Only do the rounding after you divide by the smaller of the two. Then you can do some rounding, okay? Really, that's why we talked about sig figs and all that earlier, is because it really plays a part. If you just rounded this to 1 and 3, you'll get the wrong answer. If you rounded it to 1 and 4, you get the wrong answer. So we can't round at this stage. So now divide by the smaller. So let's do the phosphorus first. 1.409 divided by 1.409. That's going to give you 1, right? And let's do the oxygen next. Oxygen, 3.5225 over 1.409. And that's probably going to give you a fraction. Let's see what we get. 3.5225 divided by 1.409. It looks like you get 2. Oh, actually, it came out exactly 2.5. Okay. All right. So remember what we said. At this stage, if you get something that's pretty close to 0.5, like 2.49, 2.49. 2.49 is close to 2.5. You're going to have to multiply everything by 2. So just multiply everything by 2. So for phosphorus, you got to multiply both of them so that the ratio stays the same. For oxygen, 2.5 times 2 equals 5. Okay. So here we go. We got 2.5. That's our empirical formula right there. So the empirical formula from that would be P2O5. Remember, it's got to be a whole number at this stage. Okay. Last step, molecular formula. How do we do the molecular formula? We take the given piece of information. That's got to be given to you. That's not something you can figure out on your own. Someone measured it using a laboratory technique. That's why it was difficult until the 20th century for people to figure out the formulas, the actual chemical formulas, the molecular formulas. They didn't have ways to figure out the molar mass. We have all kinds of techniques now. So now what do? You take that molecular formula, the molar mass of the molecular formula, and the way I wrote it before was you take MF over EF, right? So you take your 283.89 grams per mole, and then you divide that by the molar mass of the empirical formula. So let's calculate that. That's right here. For the empirical formula, it's 2 times 30.97 grams per mole. That's from the periodic table. 5 times 16 grams per mole. So 2 times 30.97 plus 5 times 16, and you get 141.94 grams per mole. Okay, so 141.94 grams per mole. Do the ratio. 283.89 divided by 141.94, and you get 2. Right? There's a bunch of zeros, so you can round that to 2. If you get 2.00000, that's definitely 2. So round that to 2. What that tells us is the actual formula is 2 times as heavy as the empirical formula. So if the empirical formula is P2O5, multiply that by 2. So I'm going to take this number here, multiply it by 2, and you get P4010. And there's your molecular formula. Okay, you're done with the molecular formula. That's it. Okay, so that's the 2 types of problems in this section of 3.5. So one is finding the empirical formula, which they call elemental analysis. The other one is finding the molecular formula from the molar mass. The only thing that really varies is how many elements you have. So it could be done with 2 elements. It could be done with 3 elements. It could be done with 4 elements. Generally, in this type of course, we do it with 2 or 3 elements, but it's essentially the same thing. So 2 types of problems in this. There is, as I began at the beginning, there's an issue with the writing the chemical equations, but that's fine. We already went over that. Okay. So next week, technically next week is a holiday. It's Memorial Day, but I'm going to go ahead on Monday and record a video. So I will open the Zoom if you want to join. And I'm going to cover the next section, which is 3.6, which is calculations with balanced chemical equations. It is a little bit of an involved calculation like we did here today, but it's a different type of calculation. So I'm going to go over that next week. And then the last week, which would actually, you know what, I got to do 3.7. So I'll do 3.6 and 3.7 next week. And that's the end. That's the end of the course. We just have really 2 more types of problems and we'll be done with this. And I will do it then. So good luck. I'll have this posted today. Good luck with everything. Make sure that you're working, put some effort into these problems because there's a lot of steps. As you saw, that empirical formula had 5 steps, and then the molecular formula had an additional 2 steps. So it gets up to 7-step problems. So these get pretty involved. So have a great day. Have a great week. And let me know if you have any questions. And take care. Be well.
Bye, Professor. Bye.